In this video, we're going to have a look at the properties of ionic compounds, and I started by drawing out a particle model for a solid, a liquid, and a gas. A common question is you're asked to predict what state an ionic compound would be in at room temperature. And so we need to look at the different particle models so we can decide which one will fit an ionic compound. In a solid, you will see that the particles are very tightly packed together. The fact that those particles are so tightly packed tells me that those particles are strongly attracted to each other. If we look at a gas, the particles are really far away from each other. This tells me that the particles are not attracted to each other. So I'm looking at ionic compounds. I need to ask myself, what particles do I have present, and are they strongly attracted to each other? In an ionic compound, we saw in the previous video that you have got oppositely charged ions. So if I had sodium chloride, I would have positive sodium ions, and I would have negative chlorine ions. They are the particles present in an ionic compound. Are these particles strongly attracted to each other? The answer is yes. Oppositely charged ions are really strongly held together by the electrostatic force of attraction, and if the attraction between the particles is strong, then they are going to exist as solids at room temperature. So all ionic compounds are solid at room temperature. The particles are strongly attracted to each other, which means the particles are tightly packed. If I wanted to go from a solid to a liquid, we know that state change is called melting. And when you go from a solid to a liquid, what you're actually doing is you're pulling those particles apart. You'll see in a liquid that those particles, although they're still touching, they are further apart than they were when they were in a solid. In order to do this, you're going to have to put energy in. You're going to need to put energy in to break those forces in the solid so that you can pull the particles further apart in a liquid. How much energy are you going to have to put in? Well, if the forces holding those particles together is really, really strong, you're going to need lots and lots of energy to overcome those forces and pull those particles apart. Sodium chloride, held together by the electrostatic force of attraction. Again, that electrostatic force is really, really strong. So if I want to go from a solid to a liquid, I'm going to need to put lots and lots of energy in to break the really strong electrostatic force of attraction and melt my ionic compound. So ionic compounds, property number 1, they are solid, and we can also say that they have very high melting points. The second property you need to know is about conducting electricity, In order for anything to conduct electricity, any substance to conduct electricity, there are two criteria that they must meet, They must have some sort of charged particle, and that charged particle must also be mobile. That charged particle must be able to move around. So question number 1, do ionic compounds have charged particles? Well, we've just seen here that the individual particles in ionic compounds are ions, and ions are charged. So in sodium chloride, you've got positive sodium ions, you've got negative chlorine ions, so you do have charged particles in ionic compounds. Those charged particles are ions, A common mistake here is people write delocalized electrons. Delocalized electrons are charged particles, that is true, but you don't find them in ionic compounds. The charged particle in ionic compounds are ions. The next thing we need to ask yourself is, are those charged particles mobile? Are they free to move? We're going to go back to our particle diagram. In a solid, you should remember this from GCSE, that the particles cannot move freely. They are held in fixed positions and they can only vibrate. So if you have a solid ionic compound, which we said is how you find them at room temperature, although you've got charged particles, those charged particles can't move, and if they can't move, they cannot conduct electricity. If you did melt your ionic compound though and put it into liquid form, you would still have your charged particles, you would still have your ions, but in liquid form, those charged particles would be able to move, and therefore they would be able to conduct electricity. There are two ways to get an ionic compound into liquid form. We've mentioned one already. You can melt an ionic compound. The second thing you could do would be to dissolve it in water. So I'm going to write that they do conduct electricity, but only when molten, which is just another word for melted, or aqueous, which is dissolved in water. They have the charged particles, ions, they always have ions, but those ions can only move when it is a liquid, so you're going to melt them or you're going to dissolve them in water. Okay, the third thing we need to look at is solubility. So I talked above about dissolving your ionic compound in water. We need to look at exactly what affects solubility. With this, I'm just going to show you the following diagram. Okay, so solubility is, in fairness, quite hard to predict. So in the beaker above, I have put, or the picture shows that you're putting some salt into water. Okay, and this picture here represents what's actually happening when you put the salt in the water in terms of particles. So you see here, you've got your salt as a solid. So they've depicted the ionic compound here as a solid in a 3D lattice. And this solid is surrounded by individual water molecules. And what happens is that these water molecules themselves are attracted to the ions in your ionic compound. And what these water molecules will do, they'll surround the individual ions in the ionic compound, and then they will separate the ions from the rest of the ionic compound. If it completely dissolves, like what you've got here, you'll see all of the ions have been completely surrounded by water molecules, and those water molecules have separated the ions from each other. So you end up with all of the ions totally separate, surrounded by water molecules. Because those ions have all been separated, they're behaving as if they were a liquid. So the solid, you can no longer see, because those ions aren't bonded together anymore. Those ions have all been separated. Because they're separated, they no longer look like a solid. They are dispersed amongst the liquid, and you can no longer see it as a solid. And that's what's happening when they dissolve. Okay, so in order for this to happen, okay, there has to be an attraction between the water molecules and the ions. Okay, we already know that a really strong attraction exists between the ions themselves. Okay, that attraction is hard to overcome, and water is only going to be able to overcome that attraction if the ions are attracted to water molecules themselves. Okay, some ionic compounds will dissolve, some won't. Okay, there are other factors in place, but in general, you need a strong attraction between the water molecules and the ions that's strong enough to overcome the attraction between the ions themselves. If we look at this table, we see the solubility of some different ionic compounds. Okay, you'll see that if you have sodium chloride, okay, that you are getting, it has a solubility of 6.1 moles will dissolve per litre. If we go to calcium chloride, it's less soluble. And if you look at sodium carbonate, it's more soluble than calcium chloride. And then you've got calcium carbonate, which is less soluble again. Okay, so some ionic compounds will dissolve quite well, others will not dissolve quite as easily. And there is actually one thing that I forgot to mention, actually, that will help explain that table. Okay, when we're looking at the attraction that exists between ions, okay, we said the strong electrostatic force of attraction holds oppositely charged ions together. Okay, if we look at this ionic compound, sodium fluoride, the ions present are Na plus and F minus. If we look at the next one, calcium fluoride, you've got a Ca2 plus ion and an F minus ion. The higher the charges on the ions, the stronger the attraction between them will be. So if we look at NaF, okay, where you have got a positive sodium and a negative fluorine, if you compare that to CaO, where you've got a 2 positive charge on the calcium and a 2 minus charge on the oxygen, the attraction between them, between the 2 plus and the 2 minus, is much greater than between the 1 plus and the 1 minus. So the greater the charge on the ions, the stronger the attraction between them. Because this attraction is so much stronger between calcium and oxygen, it requires a lot more energy in order to pull those ions apart when you are melting. Okay, so the melting point for calcium oxide ends up being a lot higher than the melting point for sodium fluoride. Okay, that can be seen in this table as well. Okay, the higher the charges, the stronger the attraction between the ions. That means it's harder for the water molecules to come down there and separate the ions. So you'll see when you had a +1 and a -1 charge, the solubility was relatively good. But when we come here to a +2 and a -2 charge, it was far, far less soluble. Okay, this is because the attraction between the ions and the water molecules is no longer strong enough to separate those ions from each other and pull the ions apart. And the reason that attraction is not strong enough is just because the attraction between the ions themselves is so great. Okay, in the next video, I'm going to go through the answers to exercise 2, which is on page 23. If you haven't already, have a go with those exercises yourself and then go to the next video for the answers.